Hey there, and welcome to Waves. So we are going to start this unit, and I know it's going to be separated by February break, but um, the second half of the unit is actually a lot more interactive and fun. So we'll get through this part before we leave for break, and then hopefully, when we come back, we'll be ready for the more fun activities. In the meantime, we're just going to do some notes today, and then tomorrow is a web quest, and Thursday we are going to get into a lab, which is going to be kind of fun. We're going to use slinkies in the lab. Um, but I just wanted to give you a basis of waves and what they look like and how to measure them, so that we can use the correct vocabulary throughout the week, and you can have a solid foundation for all the activities that we're going to get into. So, without further ado, we're going to do 2 notebook pages, and there's not going to be a ton of notes, but there is 2 things that we're going to be pasting into your notebook, and they're just going to take up 2 pages. So, I am going to just have you start 2 pages of notes, 30 and 31. On the top of 30, you're going to write transverse waves, and on the top of 31, you'll write longitudinal waves. Okay, so let's start off. What are waves? On the top of your first page in your notes, I want you to define waves, okay? Waves are disturbances that carry energy without carrying matter. So in our Arduino, we talked about how energy is transferred, and it's through waves, okay? And you can see, it says it without carrying matter. You can really kind of see that in some of these animations that I have here. This wave of people is the best example, because what you can see if you look at it kind of from afar, you see the wave traveling from left to right, but the people are moving up and down. So the wave itself is not carrying the people to the right. The wave it's only the energy that's being transferred. Okay? It's the same with any of these kinds of waves. So we'll talk about that in more detail. The first kind of waves, and this is going to go in your notebook as well, we have transverse or mechanical waves. So just write down the definition of transverse waves. And they're waves that need matter or a medium to transfer that energy. So we talked a little bit about types of energy and how some energy can travel without matter. Well, transverse waves needs matter. And examples of those are sound waves, ocean waves, ripples in water, earthquakes, and waves of people at sporting events. So just write down a couple of these examples to help you remember what mechanical or transverse waves are. Some of this is covered up, but you don't have to write this down. I just wanted you to see this. The medium or the matter, it actually goes up and down for transverse waves. So again, with these people, they are going up and down, right? But the wave itself is going this way. So the back and forth or up and down is at a right angle to the way that the wave is moving. The wave is moving this way, and the people are moving up and down. Oops, up and down. So it's at a right angle to that wave. Okay, so parts of the transverse wave. Before we get into that, I want you to paste this into your notebook. Actually, it goes like this. We're going to label and define each of these parts, okay? The first, when you're ready, the first part is the crest. The crest of the wave is the highest point. So that's going to go up here, the crest. And right here, obviously, this is the highest point of the wave. Okay? Next, we have the trough. I just can't get myself out of the way here. The trough is the lowest point in the wave, and that is down here. Trough. So you can write the definitions right next to and below, or wherever you can find room. Okay, and then we have a wavelength. Again. Okay, so the wavelength, which is up here, this is the horizontal distance between either the crests or the troughs. So from crest to crest or from trough to trough, that's one wavelength. Then we have the amplitude. The amplitude is indicated here. The amplitude, and there's a lot here, so if you wanted to write amplitude, I mean, it's good that it's on the bottom because you can continue on below. The amplitude, I do want you to write all this stuff down because it's all very important. The amplitude is the measure of energy in a wave. This is how we measure how much energy the wave has. So greater amplitude is more energy. And the amplitude is the peak of a wave, and that can be either in the trough or in the crest. So it's either the negative or positive peak. It's just the highest value in the wave. It's the distance from this rest point, which is the last thing you're going to indicate here. This is the rest point. So it's from the rest to either the crest or the trough, the highest point. So the rest point goes right through the center of that wave. Oops. Okay, and you don't have to copy this down, but I just wanted to give you a visual of this. An ocean wave is an example of a transverse wave, which you should already have in your notes. And you can see that this is where the water level would be if it was actually a still day. Okay, if the water was not wavy, it would be at this middle level. And then you have the full wave height is from, which we don't really need to know about this, but from the crest to the trough, this is the full wave height. But the amplitude is just from this rest level to the crest or the trough. And then we have a wavelength from crest to crest here. Okay, so now we're going to get into compressional or longitudinal waves, which is this guy. Oops. So paste it in this way. Actually, I don't think it matters, but so in compressional waves, the medium moves back and forth along in the same direction. So you can see, there we go, in these animations that the wave is moving this way and the medium is moving like back and forth in the same direction. This is how sound waves move. And a slinky is a really good illustration of that. So if you, and we're going to play, like I said, we're going to play with slinkies a little bit later in the week. So if you move the slinky back and forth, the wave kind of moves with it. So this is a really good illustration of how the compressional wave moves. Oh my gosh, I keep doing it. Okay. So parts of a compressional wave, the compression, which is the part that's tightly wound, so right here. This is where the particles are crowded together. Now, there's showing lines in this wave, but it's mostly just, it's going to be in particles. Next, we have the rarefaction, and that's where the wave loosens. It's where they spread apart. A rarefaction. And then we have a wavelength. And a wavelength, again, is the distance from either the compression to the compression or the rarefaction to the rarefaction. So it's one full length of the wave. Just like with the peaks and the troughs, or the crests and the troughs, it's from one of the same. And I just wanted to show you this visual. This is sound. So this is a drum. And this just shows you some molecules that make up air. And then when the drum is hit, the compression that this is how the sound wave leaves the drum and travels through to your ear. All of the molecules start to vibrate, and that energy gets transferred from molecule to molecule, and then the compressions occur, and then the rarefactions is when they spread back out. So it's like vibrating up towards your ear, essentially. Okay. So underneath this, I want you to write down these last two things. We're going to write down frequency, and I'll put this up a little bit so you can see how to spell that. Oops. Frequency is how often any wave appears. It's the number of wavelengths, and it's measured in hertz. So 1 full wavelength would be a frequency of 1 hertz. And we're going to do some calculating of speed of waves today too. So I want you to write down this formula. The wave speed, and the unit would be meters over second, is the frequency, so it's how many waves appear, times the wavelength in centimeters. So now that we're done with notes, we're going to switch over to this page here. And you're going to attempt to do this on your own. Now, of course, I'm around if you have questions, but I'm just going to read through it quick so that I can hopefully answer questions before you even have them. So this is so you can understand wavelength, frequency, and amplitude and how they're related to wave energy. First, you're going to write the frequency of each wave in the series, remembering that each wavelength is a frequency of 1. So after you figure out how many, well, let's do A together. How many do we have here? 1 wavelength is from crest to crest, so you have 1. And then after you're done with that, a series of waves above has the greatest frequency, has the lowest frequency, and so on. Okay. Next, we're going to measure the amplitude, and I put this in a graph form. You guys are very used to graphs at this point, or you should be. And you can see that on the x-axis is the distance, and on the y-axis is the amplitude. Okay? So you're going to figure out the wavelength, which is in centimeters, so that's the distance, the amplitude, which is also in centimeters, and then based on that, the frequency. Part 2 is not copied in here for some reason. Hold on 1 second. Part 2 we have right here on your paper. You're going to figure out on here the wavelength, amplitude, and frequency again. And this time it's not giving you numbers on your x or y axis, so you just have to count. Each square is a centimeter. Okay? Each block is a centimeter. And then using the formula for speed that we just put down in our notebooks, you're going to calculate the speed once you know the amplitude, the frequency, and the wavelength. Okay? Part 3, you're going to sketch your own. Now you're given amplitude and wavelength, you're going to sketch your own. And the way to do this, because if we travel back up here, we know that amplitude is on the y-axis, distance is on the x-axis. So the first thing you want to do is start to sketch out your dots and then connect the dots. Okay? You are going to, just because this only has 1 unit here, it doesn't mean that you're just going to do 2 dots and be done. You're going to keep on going. So every 4 centimeters, you're going to indicate the amplitude of 4. So it's actually kind of the same as here. A dot would be here. And you're going to travel over to the wavelength. Okay? And then finally, taking all that you've figured out so far, you're going to indicate if frequency increases, what happens to wavelength. If frequency decreases, what happens to wavelength. So again, this is just kind of tying in all the stuff that we know. And once you're done, or if you have any questions before you finish, let me know. All right, good luck.